Welcome back to the class. In today's class, we'll be learning about pointers. Which feature of C do beginners find most difficult to understand? The answer is easy. Pointers. Other languages have pointers, but few use them so frequently as C does. And why not? It is C's clever use of pointers that makes it the excellent language it is. The difficulty beginners have with pointers has much to do with C's pointers terminology than the actual concept itself. For instance, when a C programmer says that a certain variable is a pointer, what does that even mean? It is hard to see how a variable can point to something or in certain direction. It is hard to get a grip on pointers just by listening to a programmer's jargon. In our discussion of C pointers, therefore, we will try to avoid this difficulty by explaining pointers in terms of programming concepts we already understand. So the first thing you'll be looking into is pointer notation. Consider the declaration int I is equal to 3. This declaration tells the compiler to reserve space in memory to hold the integer value, to associate the name I with this memory location, to store the value 3 at its location. We may represent I's location in memory by the following memory map. We see that the computer has selected memory location 65524 as the place to store the value 3. The location number is not a number to be relied upon because some other time the computer may choose a different location for storing the value 3. The important point is I's address in memory is a number. We can print this address number through the following program. The output of the above program would be address of I is equal to 65524 and value of I is equal to 3. Look at the first printf statement carefully. The ampersand is used in the statement in C's address of operator. The expression ampersand I returns the address of the variable I, which in this case happens to be 65524. Since the number 65524 represents an address, there is no question of a sign being associated with it. Hence it is printed out using %u, which is a format specifier for printing an unsigned integer. We have been using the ampersand operator all the time in the scanf statement. The other pointer operator available in C is the asterisk mark called value at address operator. It gives the value stored at a particular address. The value at address operator is also called as indirection operator. Observe carefully the output of the following program. Note that printing the value of asterisk with ampersand I in brackets is same as printing the value of I. The expression ampersand I gives the address of the variable I. This address can be collected in a variable by saying j is equal to ampersand I. But remember that j is not an ordinary variable like any other integer variable. It is a variable that contains the address of other variable, I in this case. Since j is a variable, the compiler must provide its space in the memory. Once again, the following memory map will illustrate the contents of I and j. As you can see, I's value is 3 and j's value is I's address. But wait. We can't use j in a program without declaring it, and since j is a variable that contains the address of I, it is declared as int asterisk j. This declaration tells the compiler the j will be used to store the address of an integer value. In other words, j points to an integer. How do we justify the usage of asterisk in this declaration? Let us go by the meaning of asterisk. It stands for the value at address. Thus, int asterisk j would mean the value at the address contained in j is an int or an integer. Here is a program that demonstrates the relationships we have been discussing. The output of this program would be work through the above program carefully, taking help of the memory locations of I and j shown earlier. This program summarizes everything that we have discussed so far. If you don't understand the program's output or the meanings of ampersand I, ampersand j or asterisk j, and asterisk with ampersand I, go through the last few slides. Everything we say about C pointers from here onwards will depend on your understanding these expressions thoroughly. Look at the following declarations. Here, alpha, ch, and s are declared as pointer variables, that is, variables capable of holding addresses. Remember that addresses, that is location numbers, are always going to be the whole numbers. Therefore, pointers always contain whole numbers. Now we can put these two facts together and say Pointers are variables that contain addresses, and since addresses are always whole numbers, pointers would always contain whole numbers. The declaration float asterisk s does not mean that s is going to contain a floating point value. What it means is s is going to contain the address of a floating point value. Similarly, character asterisk ch means that ch is going to contain the address of a character value. Or in other words, the value at address stored in ch is going to be a character. The concept of pointers can be further extended. Pointer, we know, is a variable that contains address of another variable. Now, this variable itself might be another pointer. Thus, we know how a pointer that contains another pointer's address. The following example should make this point clear. The output of this example would be, this particular memory map would help you in tracing out how the program prints the above output. Remember that when you run this program, the addresses that get printed might turn out to be something different from the ones which are shown in this particular figure. However, with these addresses too, the relationship between I, j and k can be easily established. Observe how the variables j and k have been declared. Int I asterisk j double asterisk k. Here, I is an ordinary integer. J is a pointer to an int, often called as an integer pointer, whereas k is a pointer to the integer pointer. We can extend the above program still further by creating a pointer to an integer pointer. In principle, you would agree that likewise there could be existing a pointer to a pointer to a pointer to a pointer to a pointer. This is no limit on how far we can go on extending this definition, possibly till the point we can comprehend it. And that point of comprehension is usually a pointer to a pointer. Beyond this, one rarely requires to extend the definition of a pointer, but just in case. Next, go into function calls. Having had the first tryst with pointers, let us now get back to what we had originally set out to learn. The two types of function calls, call by value and call by reference. Arguments can generally be passed to functions in one of the two ways: sending the value of the arguments, sending the addresses of the arguments. In the first method, the value of each of the actual arguments in the calling function is copied into corresponding formal arguments of the called function. With this method, the changes made to the formal arguments in the called function have no effect on the value of actual arguments in the calling function. The following program illustrates the call by value. The output of this program would be x is equal to 20, y is equal to 10, a is equal to 10, and b is equal to 20. Note that the values of a and b remain unchanged even after exchanging the values of x and y. In the second method, call by reference, the addresses of the actual arguments in the calling function are copied into formal arguments of the called function. This means that using these addresses, we would have an access to the actual arguments, and hence we would be able to manipulate them. The following program illustrates this fact. The output of this program would be a is equal to 20 and b is equal to 10. Note that this program manages to exchange the values of a and b using their addresses stored in x and y. Usually in C programming, we may call by value. This means that in general, you cannot alter the actual arguments. But if desired, it can always be achieved through a call by reference. Using a call by reference intelligently, we can make a function return more than one value at a time, which is not possible ordinarily. This is shown in the program given below. And the output for this program would be, enter the radius of circle 5, area is so and so, and perimeter is 31.4. Here, we're making a mixed call. In the sense, we are passing the value of radius, but addresses of area and perimeter. And since we are passing the addresses, any change that we make in value stored at addresses contained in the value a and p would make the change effective in main. That is why when the control returns from the function area peri, we are able to output the values of area and perimeter. Thus, we have been able to indirectly return two values from a called function and hence have overcome the limitation of return statement, which can return only one value from a function at a time. So the conclusions from this would be, if we want that the value of an actual argument should not get changed into the function being called, pass the actual argument by value. If we want the value of an actual argument should get changed in the function being called, pass the actual argument by reference. If a function is to be made to return more than one value at a time, then return these values indirectly by using a call by reference. With this, we have come to the end of our class. In the next class, we'll be learning about recursion. Thank you.